Good afternoon, good morning, everyone. Good evening. This is Landscapes Live this week, hosting Dan Parsons. Probably many of you know him from maybe his time as the division president of geomorphology at EGU. Dan hails from the UK. He obtained his PhD at the University of Sheffield in 2004. Moved across different institutions in the UK. Dan, I'm sorry, I'm not going to go to do the full CV for you, but now is at the Loughborough University. And importantly, he was our president at the EGU for the geomorphology division. And I'm going to just post something in the chat for everyone in the meeting. He participated in a really cool group interview with the different previous presidents of the GM divisions that is now led by Kristen Cook. There's, I think, two parts in that interview, and you get a pretty good insight into how the division came to be. And this is, of course, our main partner and sort of like an umbrella for Landscapes Live. Having said that, as you know, this meeting is recorded. It will be posted on YouTube afterwards. What's going to happen is that Dan will talk for 35, 45 minutes, depending on the presentation length. And towards the end of that, we will open the chat so you can all start typing in your questions. When Dan is done, we will read the questions aloud, and we will have the discussion continuing like this. Dan, the floor is yours.
Thank you so much, and thanks so much for the invitation to speak at Landscapes Live. You're quite right. I was division president at the EGU when Landscapes Live was born, right at the I guess the nexus of the impact of the global pandemic, and I think Landscapes Live is just one of those phenomenal things that came out of that strange time in all of our lives. But what was so great about how it worked through the pandemic was the way in which it provided that conduit for us all to come together as a community, and it's proved its purpose both then, but also the way in which it's continued to flourish. And so it's a great pleasure for me to come and talk to you about some of the science that I've been involved with, and with a big team of people that we'll get into and talk through what we've been finding and some of the outcomes and the impacts of the science as well. And after 6-7 years of doing a whole range of things around the presidency of EGU, of the division, and sending you so many messages about the logistics of meetings, it's actually really nice to come and talk about some science and share that with you. So thank you. So I'm going to be talking about evolving flood hazard and risk, and the role that channel morphodynamics play in that hazard creation, but also how that hazard translates into flood risk as well. This is a part of a really big project that I'm the principal investigator on, along with Steve Darby in Southampton, but it involves a whole team of people in Oxford, in Bristol, and in other universities across the UK, as well as some collaborations internationally as well. So it's a big platform funding grant from the Natural Environment Research Council. So it's one of the big large research grants that they fund. So very pleased to have been awarded this, and thank them for the funding as well. If we start off with a broad introduction around flooding, just to take us all into that space for a moment. Each and every year, over 300 million people globally are affected by flooding around the world, and that happens every year on average. And that leads to loss of life, as we know, poor physical and mental, and poor physical health and well-being as well. And if you take that 300 million people and try to quantify that, that's close to the entire population of the USA. So that scale of order of people that are impacted every year by this hazard at Earth's surface. Sure, most of you know that the financial impacts from flooding are colossal, and again, the annual losses exceeding on average $60 billion US, which is a colossal sum that is invested or spent or is impacted as a result of flood events around the world. We also know through global heating and the impacts that will have on our climate that the risk of flooding is expected to at least double from outline projections as a result of that heating, a warmer atmosphere. And of course, what that will do in turn is expose a greater number of people and assets to these types of hazard. Critically, there's an inequitable distribution of these impacts globally. So flooding happens, of course, in all sorts of places around the world, from all sorts of different types of flooding, from pluvial to groundwater driven to coastal driven flooding, as well as the riverine flooding we'll be talking about here today. But lots of the impacts of flood hazard as it results in flood risk, on risks being realized, that they tend to impact people who are less able to recover, less able to respond to the events as they happen. Within this context, a suite of tools have been developed and delivered over a number of years now that seek to model global scale flooding. So that's flooding across the globe in various systems through the riverine systems of the globe. And these global flood models are now widely employed. They're widely employed tools for attempting to both predict, but then also for managing flood hazard and risk as well. And there's a few images there on the right to give you a flavour of the sorts of images that many of us will have seen in that true Technicolor news broadcasts that we see around the world, where people are impacted by these hazards. Now, these are the results that you would plot from these types of global flood models. This is the Caesar list flood model, and taking all different types of river system from different areas around the world where those models been deployed. You can produce maps of here the 1 in 100 year flood inundation extent, showing the complexities, the morphologies, the topographies of these river channels, and the ways in which different flood inundation happens within their domains. And these models do a good job of picking out the principal patterns of flood inundation as a result of different reoccurrence interval floods down and through systems. And indeed, as the topography the models are based upon has improved and continue to improve, the fidelity by which both spatially and temporally flood patterns can be predicted has improved as well. So there's been some revolutionary advances over the past 20 years that's improved the topographic representation that these models are run through, and phenomenal advances being made in the predictive capacity and power of these models in complex terrains like these in front of you now, urban topographies, for example. And indeed, that can come down to even street level inundation maps. And of course, lots of people are interested in these types of predictions, least of all the insurance industry, where premiums and financial models and loss models are informed by some of these, but of course also real estate agents through to people procuring property need to understand the risks associated with the location of their assets. Now, I think it's fair to say that we are now actually really good at predicting flooding a week next Tuesday. That short temporal horizon around predicting flooding is done really well. These are some flood models by colleagues here in Loughborough with a university spin-out company called Provisico that do real-time flood mapping even, and that's used for city response and emergency recovery response in cities around the world now. And our predictive power for those short time horizons based on river levels or weather pattern data are incredibly robust and do a really good job most of the time. However, when we think about global flood models over bigger domains and over longer time, that some of those predictions and their how robust they are tends to fall away. And that's because we ignore or perhaps misrepresent within these types of models a whole range of processes that are important. So channel conveyance capacity and the ways in which morphological change happens through these systems, particularly when we're looking at channels over a longer period of time, i.e. beyond the week next Tuesday, when we start to be concerned with predicting flooding in years to decades from now through these systems and understand evolving flood over a longer period of time. Factors such as channel conveyance change due to morphological change needs to be incorporated within these systems. And indeed, some more recent work I've been involved with and has been led by Josh Wolstenholme here at Loughborough has begun to show how even within event morphological change can have an impact on flood inundation extents. Now, that's important because most of our models don't incorporate those processes at present. So understanding that is really important, and lots of the work that we're doing within this project that I'll show you over the next few slides will show how some of these advances are being shown to have a really big impact and difference on flood risk. We also ignore channel floodplain connectivity processes, so the movement of water out of the channel into the floodplain and back in is really highly simplified. We normally assume some sort of uniform roughness that we know is not correct. We ignore in lots of cases the impact of dams on river systems. The river network and the type of river is excluded. So you saw on the images previous of different river systems from say the Paraná in one side and the MR River in another, being very different in terms of their morphological expressions, and again has an impact on that flood hazard propagation piece. And then finally, when we're thinking about flood risk and its transition to flood hazard, we tend to ignore dynamic population change. So we assume static populations, whereas if we're predicting effectively into the future how river channels are evolving in terms of their evolving hazard associated with flooding, what we also need to do is understand how dynamic flood risk is changing, and dynamic flood risk needs to take into account how populations are changing around the world as well. So if we go back to the outline projections of flood risk doubling by 2050, there's no real appreciation of how population centres are going to change into the future, incorporated within those sorts of projections at the moment. So again, within this project, what we're looking at is both dynamic and evolving flood hazard, but also dynamic and evolving flood risk as well. No, I'm not turned off my notifications, sorry, so if things pop up, you get to see what people are contacting me around. Okay, so we know from work over a number of years that the ability of rivers to convey flood hazards or floods changes over time. And this is some work that Louise Slater, who's part of the project, leading on one of the work packages, has done a number of years ago now. And that work demonstrated and was, you know, some of the inspiration behind the work that we've carried forward through the Evo Flood project, and showed that channel change can be a first order control on flood hazard. So this work on the US, looking at gauges across the US, the USGS and NOAA gauges network, that showed that the impact of channel change on flood hazard frequency was of the same order of hydroclimatic effects. And that is changes in rainfall patterns, or the impact of rainfall change, was of the same order of channel change and how that impacted flood hazard frequency. And of course, what that clearly shows, and what we know, is that this is ignored in current prediction. So a first order control on flood hazard is presently ignored in the way in which we predict floods, which we felt was a significant research gap that needed to be filled, hence the project. And if you look at these, hopefully this will play, yeah. If you look at rivers over time and these mesmerizing images, this is some work from Andrew Nicholas, again at Exeter, who's involved in the project, where his H-star model, which is a key element of our overall project, is able to capture these dynamic morphological changes within a numerical routine that map quite closely to what you'd see on a Google Earth engine crop of a location on Earth of interest to river geomorphologists, where you see cut-off formation, mid-channel bar migration. These channels are changing in terms of their size, their shape, their location over time, and we know that has an impact on how much water the channel can convey in certain circumstances. So by incorporating that within a channel system, where we can model everything from a single thread river through to a multi-thread river system, and capturing those morphological changes within that modeling simulation, was a really powerful tool to start thinking about and playing with conveyance capacities of channels and their relationship to morphology and morphodynamics as well. Going to move on. I can watch these play back and spot different things all the time. We should move on. So what we're trying to do within the Evo Flood project as a whole is take something like the richness of the H-star model that I've just shown you, and then start to look at things around the H-star output that would tell us about how a change of morphodynamics would impact channel conveyance capacity. And then from that, the simplification, I guess, of the richness of that 4-dimensional data, come up with a 1D channel evolution model that we could drape into a global river network. So what that would allow us to do is start playing with parameters that could be important for morphological change over time, and be able to incorporate those morphological changes in changes through a 1D channel evolution model just on channel conveyance capacity. So we're able to begin to simulate across the globe how channels are going to change in terms of their conveyance capacity, the amount of water that they can convey, and we can drape that into all of the rivers above a given size, say 20-30 meters, around the world, and then begin to incorporate over longer term simulations how river channel capacity, that conveyance capacity, how the morphodynamics were evolving implicitly within the model system. So when we begin running these simulations over multiple years into the future, through various scenarios, or building a 1 in 10, 1 in 50, 1 in 100, 1 in 200 event down through a system, dynamically coupling that to how the rivers are evolving morphodynamically as well. So what we've been able to do here is bring together all sorts of data in order to do that. We've created, I'll say a few words about this in a moment, something called GRIT, which is a new global river network that is at 30 meters globally. So all the channels around the world globally captured, but it critically includes bifurcating river reaches. So those confluence diffluence units that we know are important in big river systems. We've been able to incorporate things like Fathom, new global 30-meter digital terrain model data led by folks at Bristol who were involved in the project. So Jeff Neal, Lawrence Harker, and others. Incorporating information about bank heights, and then bringing together climate data into the future, so future scenario projections that we can then change the hydroclimate that we're feeding into our models. Taking things from storylines, so some of the work that Hannah Cloak has led on from Reading is looking at pathways or storylines through river systems over time. So what's the likely scenarios, the most plausible scenario for given river systems based on economic development, dam creation, land use change? And we know all of these things impact the river systems and how they convey water. But of all of those degrees of freedom, what are the most plausible ones? And can we narrow down using storylines the amount of parameter space that we need to explore with our modeling? We've done some flume experiments from the team at Hull, so Stuart McClelland and Pauline Del Rome, who's based there previously as a postdoc, done a suite of flume experiments that are coupled with the morphological modeling that Andrew Nicholas is doing to look at those morphodynamic expressions of flood events moving through the systems, how they reset or change the channel sizes over time as well. And all of that has been brought together to produce a global flood model based on Fathom's framework. So the company out of Bristol, and then used a whole range of data as we move through the project to get new understanding of flood risk from dynamic people. So that's Andy Tatum and the folks at World Pop at Southampton, and then understanding vulnerability and assets in that domain as well. And overall, what that does is improve our projections and our predictions of flood hazard decades from now into the future, and really beginning to understand how flood hazard is evolving, but how that translates to flood risk across the globe. So I'll just take a couple of these and just talk you through them, the most exciting developments from my perspective that we've done. We're about halfway through the project at the moment. So GRIT is a new global bifurcating river network that we've created, and that's a vector-based model. It's freely available. I'll be able to post the links and things later, so people can use this if you're not aware of it yet. The paper's out and etc. It's the first global hydrography that's at 30 meters. It represents tributary components, and those multi-threaded rivers are all represented in there for the first time. It was created using Landsat, river mask, and an elevation, that basically coupled that together through the ways in which that elevation changed to ensure that we're capturing all of the drainage density within rivers. It's based on FABDEM, which is a much improved 30-meter global digital terrain model that shows much greater accuracy than SRTM previous derivatives. And after a range of work and testing, what we've then done is put directionality through the system based on RivGraph, that allows us to have that fully connected global bifurcating river network that's a surface that's available for people to use. And this is kind of what that looks like as you zoom in, and you can see the data set in all of its glory here, with 22 million kilometers of network, a total of 58,000 bifurcations through there, and the data is now fully available on Zenodo. The Michael Wardman's piece and the paper is published as well. So a whole range of data sets are available there for folks to use and run with. in terms of the river systems and the sub-reaches that you can then download as well. So yeah, lots of work continuing to go on, and what I'll move on to next is then how we're beginning to use that to look at reach scale attributes such as channel conveyance capacity. So now once we've got this global network that we can base our predictions on, we're then critically going to start putting an understanding around channel conveyance capacity around the world. And that's exactly what we've started to do. So Yinju Liu, who's based here now at Loughborough with myself, this is some work she did in Oxford with Louise Slater, where we've started to estimate global conveyance capacity on the river network and the topology piece, and started to then begin looking at those patterns around the world. And so just to remind folks, when we're looking at bankfull river discharge, the threshold at which water flows over bank and inundates floodplains is a key what probably in terms of flooding is probably the key metric on any river system around the world. And what's typically done within the community is assuming a 2-year reoccurrence interval within a global flood model to represent what that bankfull discharge might be. And even though we know that that's massively flawed, that's the assumption that we currently use within a whole range of our flood models. So what we're trying to do here is try to get much better and more robust estimates of what bankfull river discharge QBF, what that is, and what patterns of that parameter, how that changes in different river reaches all around the world. So we set out with a suite of questions here around what's the return period and how does that vary globally? What's the magnitude of any bias that exists within the system, and can we get hold of that bias? And perhaps most critically, the spatial patterns to that bias. And then finally, can we use methodological advancements in machine learning to actually begin to populate and begin to improve our bankfull discharge approximations and how they're applied globally as well. So in terms of the methods, and this is Yinju's work, I'm using a whole range of predictors, and the paper and the data set are available here on the QR code if you want to go to. Taking gauge data from around the world, what we can start to do is look at the inflection point in that stage discharge relationships, and start training a machine model to run through, take that learning piece, couple it back in, and begin to export what bankfull discharges are around stream gauges around the world, and that's exactly what we've gone and done. Then what we can do is start looking at those patterns around what the estimated bankfull discharge is, and then put it against the observations or the data sets, and begin to look at the train versus the test data in different parts of the world. So taking some of those gauges to train a model, and then using those to then to come up with some predictions, and then testing back, and we can see reasonably good alignment across there, that the model is performing reasonably well. But what that then enables us to do is go back in, apply that into grit, and begin to look at the patterns of these changes in global bankfull discharges. And I should critically, just go back and say, thinking about this in terms of different types of catchment as well, from tropical to arid to temperate to cold, in this case, and grouping them accordingly around the world. And what we've found around this piece is that there is significant bias in the 2-year return period of discharge. It's pronounced, with distinct patterns between tropical, arid, temperate regions. You can see the overlay there on the top right, XY plot, and then as you move down, you can see the patterns of the curves where we're looking at the density of those changes and the patterns of the biases in each of those zones. We've also found that the return period of bankfull discharge and its variability in that period increases progressively from tropical to temperate to cold to arid regions. So you see that in that middle plot, XY plot there, where you see the amplitude of the lines there, moving from tropical to temperate to cold to arid as they get peakier. So we know that from this we know that these rivers change over time. We know that there's bias in bankfull discharge. We can start to plot that out at a global scale and start to better parameterize models that then start thinking about, well, what about these changes over time? And what we've been doing in this space is then starting to do some morphodynamic modeling across this. So this is some work that we did in the Flume, in the total environment simulator in Hull, and start to look at some of the patterns of changing the hydrology, so changing the hydroclimate, and then looking at what the morphological response was to those changes. And we did this both, as I said, in the total environment simulator in Hull, with a 10-meter long, 2-meter wide channel that was a braided river system set up experimentally, and then ran different flood regimes down through those systems, and then measured the morphological response of those large flood events. And then looking at different changes in either hydraulic regime in the first phases of the work, but then also changing the sediment supply regime and looking at those responses as well, running those over a number of floods. What we were also able to do is couple that into the morphodynamic modeling numerically as well with Andrew Nicholas's work, in terms of taking that model and doing similar patterns of experiments to test and validate and check and challenge between the experimental and the numerical the experiments. And what we can do is we can start seeing long-term trends and long-term patterns in discharge and the response of the thalweg over time and the timescales of those responses. So if I just draw your eyes to some of the floods that are moving through the systems, and you can see in the red lines the sorts of responses that we were getting in terms of the thalweg depth, so the changes in the average thalweg over time in response to these variations in floods. And we can test and look at the response rate curves from these, and we can test and look at the impact that they have on channel conveyance capacity. So here, if you look, for example, we have channel elevation changes over time related to these locations, and you can see different points within the flood numbers. You get different types of flood because of the antecedent conditioning resulting to floods previous. So there's this pattern to the morphodynamics resulting from the hydroclimatological changes, if you like, that we're impinging on the modeling framework, that then result in bed topographic change that then changed the flood elevation. So a real coupled system here that we're beginning to explore, looking at the impacts of as I say, changing the flood hazards and changing the impact. So if I just go back for a second here and show you through the run 1, 2, and 3, where we had no change, versus run 2, where we increase the sediment supply, and run 3, when we decrease the sediment supply. You then see in the patterns here between run 1 in the middle of the screen, I'll use the mouse here, over time, where we've impinged these floods through the system, versus run 3, where you see this dimensional pattern moving up as channel elevations are essentially declining, versus run 3, where you see the channel elevation reducing, then perhaps responding certainly distally as sediment waves move through the system. So you see very different responses to these systems based on how much sediment is supplied to them, and that's not surprising. But what we were trying to find here was understanding the scales of the changes and then using that in order to inform our 1D model that would get plugged into the global flood model, so we can begin to understand that more fully. And of course, the richness of this data set comes through when we start looking at the ages of surfaces within the domain, and how quickly morphodynamic expression is being changed in these different river systems as well. So these are from some of the numerical experiments, I should say, and we can begin to see where we see these sorts of changes through the different runs, where we've kept sediment the same, reduced sediment, or changed the sediment supply as they move through. So again, over time here, you can see as we move through the sequence, you can begin to see the patterns, the shifts, but most importantly, the build up or the reductions in the types of regime you see. And indeed, in run 3 by this point, we're at a single channel moving through here, and whereas at run 2 we've produced that kind of braided pattern through the changes in sediment supply. We see similar things but more complicated with channel width rather than average depth, but again, spatial patterns driven by those morphological changes. So what we're trying to get to here is a way for us to take very simple parameters, width and average depth, in order to begin to populate a one-dimensional model that we would apply globally, just with some very simple parameters in terms of what might change as a result of changing sediment regime. And we've done similar things with water surface slope as well, just to say. Once we then start thinking about, putting big floods through the system and how big those floods need to be to go over bank, we can begin to understand the changes in bankfull discharge as a result of those morphodynamic changes moving through. Really excitingly, and that then begins to enable us to unlock moving to that 1D model, again, that Andrew Nicholas is leading on here, where we take a 2D high resolution modeling of a river system, understanding the uncertainty in peak change, peak stage, due to dynamic river adjustments, and then putting that into a 1D model that is able to scale bank erosion and channel depth, average channel depth shallowing or increasing, and beginning to look at over time as a result of this 1D model, if you like, waxing and waning in response to these parameters. We're able to look at trends and uncertainty in bankfull conveyance along those systems, and this is some work again that's produced by the team at Exeter, and the paper Vardy et al. is I think either published or in final production. I mentioned the laboratory experiments. I was just keen to quickly show you some of those, and I'll jump through these quite quickly. But you can see the sorts of things that we're able to capture in the image in the top left there, and work that through and begin to run different types of experiments over many days, looking at equilibrium channels versus taking sediment discharge away, and again looking at those patterns and the checking and the validating with the model in the laboratory, and using that in order to best understand some of the work that the numerical modeling is unlocking for us. And again, these sorts of data that many of you will know about, that you can repeat scan in a whole range of ways, and look in ways in which the channel evolutions So these are channel change, scour and fill, if you like, over time as the flood waves are passing through. And again, very similar to the numerical model, we can look for the patterns within that, where width or depth is impacted non-linearly by the conveyance of those large floods, and how long it takes for the rivers to readjust to the changes in the flood magnitude. And again, conceptually looking at the ways in which pre-flood topography is altered during flood, but then the post-flood recovery as well in terms of the morphodynamics. I'll skip over those, but what I was keen just to highlight on, one of the key outcomes from some of the work that we've already begun moving through is the influence of flood duration, as well as the magnitude and frequency of the flood. The duration of the flood is really coming through as important in terms of the ways in which channels are adjusting and how long they're adjusted for, in terms of those long-term trends. And some of the other work is beginning to highlight that the multiple frequent medium events can have the same impact as a rare large event. So when we think about hydroclimate changes and the magnitude frequency shifts in hydroclimate, we need to be also thinking about the morphodynamics that are resulting from those shifts over time as well. And this, I think, leaves us with a way of thinking about the flooded area, so the inundation extent, and how that changes with flood history incorporated. So that imprint of the large flood morphologically reducing flood hazard certainly over a short period into the future, particularly where a river is reduced in the sediment that's supplied downstream. Final thing I'll talk you through is just the application of the global flood model. So what we've done here is apply it to the Mississippi River to look at the 2011 event, which is a 1 in 100 year flood event or thereabouts, but employing the realistic changes to flood conveyance constrained by observations of that event. So we're looking at a portion of the Mississippi Basin. These are near St. Louis or just south of St. Louis, incorporating the Ohio and the Wabash River. And we applied the Fathom global flood model to this system. We changed the channel geomorphology by changing channel capacity to convey different return period floods. So we inverted that through using some of Jeff Neal's work. And then what we were able to do is then put different return period discharges through that flood model and use that as a basis for understanding the changes to flood frequency on that piece. So if you looked at the stage discharge curves, we can look at the actual stage gauge records at those locations. We could use those and the inflections, knowing where major, moderate flood events are, and then incorporated those pieces in an empirical analysis to look at those inflection points, similar to what I was showing you in terms of the bankfull Q discharge before. We then put through the system some simulations, a 1 in 20, 1 in 100 year flood event. I'll show you those. And then we did the bankfull return periods of 1.1 through to 10 years to represent the variations driven over the recent past before the flood. And then we compared the simulations critically to remotely sensed imagery of the 2011 major flood event. And this is what the data begin to show us. So we can validate the model using, this is the observed on the left hand side, and then on the right hand side what we've got here is the 1 in 100 year flood event for two scenarios, one with a bankfull flood return period incorporated for 1.1 years, and on the right of the image as you look is the bankfull flow return period of 5 years, and we can compare and contrast how well the system the observed versus the predictions look, and have a look at the reasons for those. But most importantly, and this is where I'm going to leave you with some future thinking, is when we look at the ways in which the inundated areas change just by changing the bankfull flood event for the 1 in 100 year hydroclimate, changing the topography of the bankfull flood. So the middle image shows you the flooding extent of 2,500 square kilometers of inundated area, and then as a result of changing the frequency of changing the bankfull return period within the model domain, you dramatically reduce the amount of flooding across the system. You can see some large differences in and around the Missouri here, and then across the Ohio Wabash plain as well. And then again, if you then take a 1 in 20 year flood event, we can start looking at those, we can begin to again see the differences between a bankfull flood return period of 1.1 to 5, again significantly reducing the flooding as a result of declining channel capacity. As you move from right to left, we see much more flooding in the middle image. So we begin to see the real impact of these. And then finally, when we take that flood hazard and risk sensitivity out, we note here that just by changing the channel capacity for the smaller versus the larger flood events, we see an increase in the flood extent by 36%, with an increase of population between the two simulations, with 163% increase for the flood events resulting in the population then being exposed. So you can see here the plots look at the population flooded for large flood events, and as you increase the channel capacity, the amount of population exposed or flooded through the simulations declines over time, and similar for inundated area as well, as you might expect. And of course, these are non-linear, so for us that's super interesting, because it's demonstrating that morphology matters. It matters a lot to flood hazard, but it also matters a lot for flood risk as well. And what this project is next moving to is incorporating this 1D channel model implicitly within our global flood modeling domains, because we've demonstrated how important it is in terms of the flood risk hazard matrix into the future. So I'm going to leave it there. In terms of a summary, perhaps I'll just leave this up for you to capture that basically changes in flood conveyance that we've seen on this event really does matter in terms of the long-term changes of channel conveyance, and morphology matters, and the changes in flood extent and exposures more sensitive to channel conveyance for lower magnitude floods, but clearly impactful across the piece. And we really need to move to a place where we're incorporating morphodynamics into our flood modeling, given the importance that morphology has on these sorts of parameters. And I'll leave it there and stop sharing. Thanks so much.
Thank you, Dan. I think you can keep it shared as well. Maybe it can illustrate some of the questions.
Sure.
I'll let Anne and Laure start reading the first question, and Laurent, you can take the second one.
Sure.
Thank you.
Yeah, we already have quite a few questions. Jan Reid is starting to ask, on the question of changing channel conveyance capacity, channels are often constrained by artifacts, bank revetments, bridges, weirs, etc. These will limit the channel wandering potential. So has this been taken into account in the flood hazard modeling?
Yes, in that they're incorporated implicitly within the global river networks. It's not been incorporated in any of our any of our numerical experiments or our physical experiments, the laboratory experiments. There, the channels have been able to move across the domains that they're simulated over. So we haven't, for example, run experiments where we've got those sorts of features in the experimental, either numerical or the laboratory senses, and looked at those interactions. You're quite right that those interactions may result in a range of different morphological behaviors that we're not capturing, and we're not capturing them in the numerical experiments or the laboratory experiments, so we're not capturing them in our parameterization of the 1D model either. So that is a weakness in terms of what the impacts might be. Of course, there's a range of work being done on levee interactions with sediment transport. There's been a range of work done with flood walls and flood protections and junction vortices and all of those sorts of things. So we know it matters, but from a global perspective on what we're trying to do here, we're taking a much more zoomed out view, believing that we're capturing significant parts of morphological processes that aren't presently represented within these modeling domains, noting that we are still simplifying many of them in order to incorporate them and make the problem tractable.
Okay, thank you.
Next up, Alejandro Dusayan asks, on the global river network, how often is it updated given morphodynamic changes, and are there any plans to go below 30-meter resolution for smaller streams or tributaries?
Yeah,
before you answer, Dan, just in the interest of time, I'm going to fold in the next question of Kieran Dunn, which also adds the point of land use change. How much of an effect do you think land use change has on evolving flood hazard, particularly in the typically data poor and more rapidly evolving parts of the globe? Or is this something that you are implicitly accounting for? So both the morphodynamic changes, the land use changes, and whether you want to go below 30 meters. Sorry, I'll let you.
Yes. No problem. So for the first question, yes, it'd be great to go better than the 30 meters, and that'll be a long-term ambition. I mean, we've all seen how incredible the ways in which our resolutions and the data sets are available. It's based on FabDem at the moment, which is 30 meters. So as soon as those sorts of products become ever more higher resolution, there'll be ways in which the grid model could be adapted and updated. The other point around changing grid over time. Yeah, that's similarly, changes are always happening, and they capture a point in time. So again, there will be plans. It's I guess bandwidth of individuals and the amount of work involved. But periodically there will be updates and need to be updates. And to Kieran's question around some of the land use changes, that was the motivation for some of the experiments, both laboratory and numerical, in that we know that sediment discharge or sediment supply from catchments is a key control on the morphodynamics, and of course land use change is one part of that, but things like dams are the other, and incorporating some of those pieces is complicated in terms of the breadth of change, which is why with the work from the folks at Reading with Hannah Cloak, we concentrated on bringing forward storylines into our scenario models. And so the next stage of this is deploying a whole range of different scenarios, both hydroclimatological scenarios, but also land use scenarios, dam building scenarios, economic development scenarios, if you like, and then capturing that in terms of the impact it has on sediment discharge. And land use can increase or decrease sediment supply. Development tends to result in an increase initially and then a fall away, particularly when dams are built as well and trap sediment load. So they're implicitly in there in terms of the storylines that we'll test out. But again, that's evolving work as we speak.
Thank you, Dan. We are reaching close to the hour, but I will just take advantage of these last few minutes to ask you more general questions, because you're someone who's talking to a lot of different stakeholders, like peers in the scientific community, but also the industry, the government agencies, etc. And you mentioned a few times the 100-year return event as one case scenario. And I was wondering if you had any comments or suggestion of how do we think about a 100-year event under a shifting baseline as we have now with climate change, and how do you communicate this to a general audience? What is a 100-year event today?
It's a great question, and you're right. I mean, the stationarity of these systems and how they're communicated is incredibly difficult to do, and we all know that we're shifting those baselines as a result of that non-stationarity. And we know that, you know, a 100-year flood event, what does it really mean with that? Now, within the model framework, that 100-year flood event just means a volume of water, and we can test and challenge that through the model domain. But when it actually hits real people, that's when it matters most. In terms of communicating with the public around a 1 in 100-year flood event, and what does it mean? I wrote a conversation article a number of years ago. I'll see if I can dig it out with Chris Skinner on this. And language is really important in communicating that to stakeholders, the public, etc. If you talk about a 1 in 100-year flood event, the immediate thought is that, well, that's 100 years away, I don't need to worry. And you can get around some of those dialogues by getting into a depth of explanation. Or you could reposition the statistics and saying that the average duration of a mortgage on a house or a loan on a house when you buy your house is about 25-30 years. And a 1 in 100-year flood event basically means that your house has a 25% chance of being flooded in the period of that loan. And I think if you position that to people, that's much more tangible. There's a 25% chance that your house is going to flood in the period of your mortgage. And that's what a 1 in 100-year flood event really means. I've found that really works with stakeholders and the public in particular, because that language really matters, and it translates to something that's closer to them and means something more to them. So my advice would be to think about the stakeholder that you're engaging with, and think about their language and from their perspective when trying to communicate with them.
Thank you very much, Dan. Do you have a few more minutes?
I can stay.
Okay,
no,
so I think
stay on for a few more minutes.
So let's just cap it with the last question, and then we'll be done.
I was just wondering, like, how do you handle roughness in your simulations? Because, like, in terms of spatial variations and temporal variations, and
we don't. So again, that's a really great question. It's probably the next weakness to go over. What's the next kind of big things? Topography's been probably the major challenge for this type of flooding, and getting better topographic data. I think what's quite interesting, of course, is depending on the scale, as you increase the topography, you're kind of capturing elements of landscape roughness, and as you get to a higher and higher resolution data, you're capturing more and more of that roughness implicitly within your model domain. But of course, we know that even at 30 meters, in terms of the floodplains, but then even in terms of centimeters on riverbeds, the roughness can change appreciably over much shorter length scales. At the moment, that's not incorporated in these types of models, but we do know that this type of flood modeling needs to incorporate those sorts of processes next, and because that's probably as we improve topography and topographic representation, roughness begins to become the biggest uncertainty driver within these simulations. So it's something, certainly the future work needs to grapple.
Okay, thank you.
Well, thank you very much, Dan. Before I stop this recording, just the occasion to tell you that next week we will host Joel Wellner from Dartmouth College with the title Erosion Showdown, Glacial versus Fluvial Erosion Rates and the Limits to Timescale Dependence. You can join us live next week or catch up with all of our talks on YouTube. And before I stop this recording, have a nice rest of the day. Have a nice evening. See you next week.